So corrosion is a type of redox reaction. Corrosion is undesirable, spontaneous gradual oxidation of a metal by oxidizing agents in the environment. So mainly the oxidizing agent is oxygen. Pure metals are something that nature doesn't like very much. Virtually always you can get to a more stable state by oxidizing metals. So metals are usually found in nature's oxides. Basically all minerals that we mine that we then purify are either oxides or sometimes sulfides, which are just sort of heavier oxygen to some extent, right? Sulfides have the same electronic behavior because they're also in the same group. I know that the sulfide ion is 2-. So generally what you see in nature is oxides and occasionally sulfides. And so if we have to reduce the metal to extract it from its ore. There's a huge amount of chemistry going on in reducing metal oxides or metal sulfides in order to make pure metals. So nature, the nature of the universe is it wants to push it back towards that. So if you put a metal out in the environment, it will start reacting eventually. Now the speed can be quite slow, but there are lots of things that can happen that can make it a lot faster. Lots of ways that reaction can be catalyzed. So yeah, that's what corrosion is. Metal is being oxidized back to its more stable state. So reduction of O2. So oxygen is very easy to reduce in moist conditions here oxygen is in the the oxidation state of 0, to reduce it down to an oxidation state of -2. So if we have oxygen plus 2H2 plus 4 electrons, if you look at the just look up on the tables, you would see that that has a standard potential of 0.4 volts. It's even easier to reduce under acidic conditions. So oxygen plus 4H plus 4E minus goes to two waters. Now, if you have acid driving it forward, that has a reduction potential of 1.23 volts. It's even more stable. So this is something that if you want to keep things from being to keep metals from being oxidized, you keep them dry and you make sure that there's no acid around. But of course, we know that water is actually slightly acidic in most cases. If you expose water to the atmosphere, it's going to absorb some carbon dioxide to make a carbonic acid, and you get a little bit of dissociation of the carbonic acid. And so actually the natural pH of water that's been exposed to air for a while is slightly acidic. So almost any conditions, pure metals are going to rust. So because the reduction of most metals, ions, lies below oxygen on the table of standard reduction potentials, except for noble metals, the oxidation of these metals by O2 is spontaneous. If we look at the table, then we can see that what is below oxygen. So at neutral conditions, what metals are above? Copper, iron, silver are all above at neutral conditions. But if you look at acidic conditions, then it's way up here. And so really gold, platinum, these are the only metals that are not going to react with oxygen at under acidic conditions. Even silver tarnishes, right? You get silver oxide. You need a little bit of acidic conditions, but you can get it to happen. Good thing is, a lot of metals, they just tarnish on the surface. And so that works pretty well. You just get a barrier like silver oxide or your copper oxide, the patinaing copper oxide. It coats it and then it protects the rest of the copper from being destroyed. So you get a little bit of copper oxide on the top, but that makes an impenetrable barrier where it's a hard time for oxygen to get in. Iron, on the other hand, is not so lucky. Iron oxide does not create a protective barrier. Okay, so corrosion of iron. This is the most common thing. You get no protective iron oxide barrier here. And it's sort of a complicated process. So the first thing to happen is the oxidation of iron solid to iron plus 2. And you usually get it inside a water droplet, like at the center of a water droplet. And so you have the anodic region there, in the center of the water droplet. It has to be an area that's roughly covered with water so that the iron 2 plus can dissolve away. And then what happens is the electrons flow through the metal to the edge of a water droplet, whereas oxygen is available. And then you have this reaction occurring where the oxygen takes those electrons that flowed through the iron. So the iron is the conductor here, as well as so it's the anode that's both being consumed and passing the electrons along to the other reaction. And there in the cathodic region, you have oxygen being reduced to form water. And then that iron 2+ floats around and undergoes additional oxidation. So now once that 2+ comes off of the surface, it's dissolved in the water. And it goes over to the edge of the water droplet, where you get that iron 2+ oxidizing additionally to the +3 state. And then rust is a combination of iron oxide plus some water as well. So that is the multi-step place of the multi-step process of iron. And you do not get any sort of protective coating like you do with silver and copper. And so moisture must be present as water as a reactant, both for the oxygen to undergo the reduction and also to transport the ions away. And yeah, iron flow is required between cathodic and anodic regions. It's not just the iron reacting, it's also the iron carrying the electrons away from a place where there's no oxygen to where there is oxygen. And electrolytes promote rusting by, if you have things dissolved in that water, it's even better. It promotes current flow for the ions coming back. So acids promote rusting, as we've seen. Increasing H+ concentration will lower the reduction potential about 2 by the Nernst equation. And so to prevent corrosion, what can you do? Well, one way to slow corrosion is to coat the metal surface. If you just paint it with a really thick, durable paint, and you'll see this a lot in ocean environments, you have a really thick paint that you put over it, that keeps it from contacting corrosive chemicals in the environment. Salt water is really bad because it's really conductive. Paint, yeah, I'm going to do it. Some metals, such as aluminum, form an oxide that strongly attaches to the metal surface, preventing the rest of the metal from corroding. So you could actually put aluminum on top of the iron, and it'll form an aluminum oxide barrier on the iron. Another method to protect a metal is to attach it to a more reactive metal that is cheap. These are sacrificial electrodes. So galvanized nails have coatings of zinc, and that zinc will be more reactive, and that will oxidize first. And so that's where you get galvanized nails, is you're coating it with zinc, and that essentially becomes sacrificial. So if you have an iron pipe, what you can do is actually physically attach another metal. It doesn't have to be just painted all over it. It can really just be on part of it. And the electrons get carried to the electrode in order for the reaction to happen there.